One and all present over here. I am Gautam Bacher from BITS Pilani-KK Birla Goa campus. I am from the IEEE department. This work is about understanding immunosensing phenomena of micro IDE-based extended gate field effect transistor supported by EIS system. So the outline of my presentation will be a brief introduction, background and motivation of the work, and then the development of extended gate field effect transistor. Then I'll share some of the results, experimental results, and followed by conclusion and the references. So it is quite well known that this field effect transistor is being used for biosensing application due to its potential for miniaturization, and it has got fast response time, and then it also facilitate fabrication processes, integrate with the fabrication processes, and but then conventionally most of the time these extended gate field effect transistor is being used with the help of a bulk electrode. The advantage with this extended gate field effect transistor based biosensor is that through this we can separate out the dry part and the wet part. So when the biosensing comes in pictures, and especially the immunosensing, you have to do the surface modifications, and then some chemical is being involved. This is a very simple structure being used where very cheap MOSFET, market available MOSFET you can make use of, and then you can do your biosensing, your chemistry part on the other side of it, so that you can divide between the two. Going to the working principle of this FET-based or extended gate FET-based biosensor, what basically happened is that wherever there is a interaction between the antibody antigen, then it creates a double layer capacitance. And this double layer capacitance basically will reduce the overall capacitance of the whole setup in a way. Or other way, if there is an antibody-antigen interaction, then the surface potential, it will change the surface potential, and followed that there will be charge modulations. And that we can see in terms of change in the effective capacitance, change in the surface potential, and as a result, change in the drain to source current. This is a schematic representation of a EG-FET-based biosensor, where we can make use of a different receptor, bioreceptor like antibodies, can be DNA-based enzyme, microorganism or cell, which typically is being attached to the surface of an electrode, which work as a extended gate of this EG-FET. Thereafter, we can connect this gate, this extended electrode as a gate, and then we can read the transfer and the output characteristics so that we can quantify this binding effect. So the background of this work is when we have the literature survey, we found that although these extended gate field effect transistor been quite being used in the literature, or it is reported, but most of the time it is for the pH sensing, especially when I talk about interdigitated electrodes. So when we talk about the biosensing, one always look for that I should make use of a very small sample volume. Why? Because this reagent or this antibody will cost you. So overall cost of the system will increase if I use a bulk electrode and all that. So to minimize the cost or to minimize the system, we go for this interdigitated electrode. But then since there was not much work on the on the biosensing side, more on the pH sensing, although biosensing side, but then they have used mostly the bulk electrode. So this work basically evaluate the use of this micro ID as a extended gate electrode, the effect of that. So these are the motivation that these people use bulk electrode, and then uh, this pH intradigit electrode is being used for the pH sensing, most of pH sensing, and the even the configuration or geometrical configuration of that electrode is not being explored much as far as this AG is concerned. So here the electrical connection diagram and the governing equations for this EG-based biosensing. So here we can look at that. You see the overall capacitance. If you look at that, that basically modulate your current IDS will depend upon the CT, and then CT that comprises of the offset capacitance of the MOSFET, now which is fixed, that is not changing, and capacitance of the extended gate electrode, that is also fixed. So once you freeze the configuration of the micro electrode, integrated electrode, the capacitance value that is fixed. So two things, C aux and C electrode is fixed. But then this double layer comes into picture when we do the biosensing. That means when the interaction happen, antibody antigen interaction happen, as a result of that, these double layer capacitance will vary. It will change. So effectively, these two, first two, that is COX and CEG, is remain constant. But then, based on the binding, based on the concentration of the analyte, the CDL will change, and that will reflect in this equation as CT, and that is how this IDS will change. So basically, that is on the another thing is this CDL will be more enough than this value, that COX and CEG, so that it can be detectable. So we have developed that immunosensor. So if you look at here, that we have used a gold micro electrode which is commercially purchased, and on that we have done the self assembly. That means what we are because this we are using as a label free biosensor. We are not using extra reagent for it, and moreover it is a non-Faradic case. Uh, Another aspect of this is that then be followed by the activations, and then we attach the antibody, and then we expose to the analyte of interest. So here in this case, we have used BSA as a model analyte. So what we can see here is that when we use that micro ID with this MOSFET configuration, and then at the different stages we have recorded the response. Then first we do the thiolation. So thiolation basically help you to create, again it provide you the resistance basically, so that you can carry out a non-Faradic measurement. So it provides insulation, and also it provides uniform uniform layer, so that the antibody can be attached to that. So here we can clearly see that there is a change of from SAM to PBBSA, that is antibody of BSA, and to the binding of BSA and anti-BSA. Again, the increase in the current or decrease in the current, that will depend upon the charge on the biomolecule. So that we have various concentration of BSAs being tested, and then we could find that as the concentration increases, the IDS value is decreasing. So there is some pattern we got, or we can characterize that as we can identify this concentration, this analyte with respect to the IDS. But then, as the question comes that what kind of or what configuration of this micro ID we should make use of. So for that, we have, because the chemistry we are doing on the micro ID side. So what we thought of that, let us test the different types of micro ID. So here in this case, we have chosen two different kinds of micro ID with different metallization ratio. One is 0.7 and another is 0.5. So basically the metallization ratio is what width upon width plus gap. So when your width and gap is same, that is essentially suppose I have taken in this case 10 micrometer, 10 micrometer. So your metallization ratio comes 0.5. So it varies from 0.1 to 0.9. Metallization ratio varies as that depends upon the gap of that micro electrode. So here we have tested two different types of micro electrode as extended gate for this configuration. So we have carried out this immunosensing phenomena on this micro ID separately, and then this is well established that with the concentration the CDL will change, and that we have validated with the equivalent circuit fitting, and we could find that the CDL, basically the double layer, that is decreasing with the concentration of the BSA. That happens because it is when you have a 11-amino methylation, then antibody and then antigen, it is modeled as the capacitor in series. So that is why effective capacitance get decreases over here. So this CDL is decreasing. So in our earlier case, we have related the CDL with the CT, overall CT, and then the current. So here also similar trend where as the concentration increases, the CDL is decreasing. That we could find over here. As coming back to that IDS, similar trend, decreasing trend we found. So we can compare this CDL and the IDS, that this CDL is part of this total capacitance. So the similar trends will be found. But here you can see here the micro ID1 and micro ID2, that two different. So we can see a drastic change, or you can say that these, if you change the configuration, you can have a better sensitivity of the measurement. So from ID1 is basically the metallization 0.5, wherein micro ID2 is metallization 0.7, because here the gap is 5 micrometer. We have reduced the gap. Even we have separately we have investigated the different geometrical configuration where we found that we can go close to the gap can be reduced, but then there is some limitation as well, because there will be effect of crosstalk and all the other things will be there. So that we have already investigated that what should be the optimum metal ratio for higher measurement sensitivity. So here also we validated that higher this 0.7 metallization ratio will give better result, better sensitivity, measurement sensitivity than the other. So here we have compared that two different concentration, and then EG-FET, which is being evaluated in terms of IDS, and then impedance-based EIS system. From there we have CDL. So both cases we found that there is some correlation, and then as the concentration increases, the current decreases, so also the CDL also decreases. And also, it can be noticed over here that the ID2 is better compared to ID1. So it is also saying that what kind of configuration we should choose for the better sensitivity or major sensitivity of the EG-FET. So conclusion, we have done the performance evaluation of EG-FET for different geometrical configuration of extended gate sensing electrode by IDS measurement in the substrate region. Immunosensing response to different BSA concentration significantly influenced by the change in the effective capacitance. For both micro ID configuration, the observed CDL values in EIS exhibit a similar trend that with respect to IDS. And we have validated this phenomena with the EIS study. Additionally, the appropriate choice of geometrical configuration of the extended gate ensures desired measurement sensitivity. These are some of the references being used in this work. Thank you so much.